Greetings everyone, welcome to E&E Learning Hub, where I'm going to go through and explain the solutions for past paper questions related to single-phase series AC circuits. All right, so let's begin. All right, so for question 6 from the 2015 past paper question, part A, it says, Figure 8 shows the circuit diagram of a coil with an ohmic resistance of 3 ohms and an inductance of 0.01 Henry connected to a 12-volt AC 50 Hertz supply. So here is figure 8, the series RL circuit. So it says calculate part 1 of A, the inductive reactance of the coil. So inductive reactance XL is equal to 2 pi FL, that is 2 pi times 50 Hertz times 0.01 Henry. That will give us 3.14 ohm. For part 2, says to calculate the impedance of the coil. So impedance Z is equal to square root of R square plus XL square equal to square root of 3 ohm square plus 3.14 ohm square equal to square root of 9 plus 9.86 equal to square root of 18.86, and that will give us 4.34 ohm, and that is the impedance of the coil. Part 3, it says to calculate the circuit current. So V is equal to I times Z. So therefore, I is equal to V divided by Z. That will give us 12 volt divided by 4.34 ohm. That will give us 2.76 ampere. So that's the circuit current. And that's it for part A. For part B, it says, briefly explain the relationship between the circuit current and the applied voltage when the AC voltage is applied across a purely resistive circuit. So that's for part 1. So in a purely resistive AC circuit, the current and the applied voltage are in phase. Part 2, purely inductive circuit. So in a purely inductive AC circuit, the current lags the applied voltage by 90 degrees. All right, so that's it for part B. For part C, it says briefly explain the relationship between the current in the main winding and the starting winding of a single-phase AC motor with a highly inductive starting winding. So that's for part 1. So in the case of an inductive starting winding, the winding has a higher inductance compared to the main winding. This causes a phase shift between the current and voltage applied to the motor. The current in the starting winding lags behind the voltage, which creates a rotating magnetic field that drives the rotor. Once the motor reaches its operating speed, the starting winding is disconnected from the circuit by a centrifugal switch. All right, so that's it for part 1. For part 2, it says capacitive starting winding. So in the case of a capacitive starting winding, the winding has a higher capacitance compared to the main winding. This causes a phase shift between the current and voltage applied to the motor. The current in the starting winding leads the voltage, which creates a rotating magnetic field that drives the rotor. Once the motor reaches its operating speed, the starting winding is disconnected from the circuit by a centrifugal switch. All right, so that's it for part C, and that's it for this question. All right, so let's move on to the next question. So that is question 6 from the 2011 past paper. Part 1 of A, it says define inductive reactance. So this is the opposition to current flow in a purely inductive circuit. Part 2, it says write the formula for inductive reactance and explain each of the terms in the formula. So the formula for inductive reactance, XL is equal to 2 pi FL. So XL is the inductive reactance. 2 pi is a mathematical constant. F is a frequency, and L is inductance. All right, so that's it for part A. For part B, it says an alternating voltage source is connected across an inductor L as shown in figure 2. So here is figure 2. Here we have the inductor and we have a voltage source connected across it. So part 1 of B, it says using a wave diagram to show the phase relationship between the voltage and the current across the inductor. All right, so here is the diagram. So for a purely inductive circuit, the current lags behind the voltage. All right, so that's what this waveform is showing us. All right, so the current, it lags behind the voltage. All right, so that's it for part 1. For part 2, it says illustrate the relationship between the current and the voltage using a vector diagram. All right, so here we have the diagram here. So on the vertical side, we have VL, and the horizontal side, we have IL, and the angle between both is 90 degrees. So remember that for the purely inductive circuit, the current logs the applied voltage by 90 degrees. All right, so that's it for part 2. So that's it for part 2 of B. So let's move on to part C now. It says an AC supply of 110 volt and 50 hertz is applied across an inductor of 0.5 Henry. Calculate the current flowing through the inductor. All right, so the first thing that we'll have to do is to calculate XL. So XL is equal to 2 pi FL, that is 2 pi times 50 hertz times 0.5 Henry. That will give us 157.1 ohm. So VL is equal to I times XL, and from that formula, we can calculate the current. So current is equal to VL divided by XL, and that is 110 volt divided by 157.1 ohm. That will give us 0.7 ampere. All right, so that's it for part C. For part D, it says define the term EMF of self-inductance. Give one application of EMF of self-inductance in electronic circuits. All right, so the term EMF of self-inductance refers to the voltage induced in a circuit due to a change in current flowing through a coil or inductor. The application, it is used in switching regulators. All right, so that's it for part D. And that's it for this question. All right, so let's move on to the next question. That is question 7 from the 2014 past paper question. Part 1 of B. It says, state the names of the two resistive effects in an inductive AC circuit. All right, so the two resistive effects are the resistance of the conductor and eddy current losses. All right, so part 2, it says, name the two types of electrical power in an inductive AC circuit. So the two types of power are 1, active power, 2, reactive power. Part 3, it says, state the name of one resistive component in an inductive AC circuit. So the resistive component is the resistor. So that's it for part B. For part C, it says figure 5 shows the circuit diagram of a resistor and an inductor connected in series to an AC supply. So here is figure 5. Here we have a resistor, 3 ohm, connected in series with an inductor of 0.0127 Henry. All right, so it says calculate the inductive reactance of the coil. So that's part 1. So inductive reactance XL is equal to 2 pi FL. That is 2 pi times 50 Hertz times 0.0127 Henry. That will give us 3.99 ohm. So that's the value for the inductive reactance. Part 2 says to calculate the total opposition to AC current flow. So we're basically calculating the impedance. So Z is equal to square root of R squared plus XL squared. That will give us square root of 3 squared plus 3.99 squared. That will equal to the square root of 9 plus 15.92. That will equal to the square root of 24.92. That will give us 4.99 ohm. So this is the value for the impedance. All right, so let's move on to part 3. It says to calculate the total current flowing in the circuit. So I is equal to V divided by Z. So the voltage was given, which is 20 volts. Z is the impedance that we just calculated, which is 4.99. And 20 divided by 4.99 give us 4 ampere. All right, so that's the current flowing through the circuit. So part 4, it says to calculate the active power in the circuit. All right, so the first thing that we'll have to do is to calculate the phase angle. So tan theta is equal to XL divided by R. So that is 3.99 divided by 3. That will give us 1.33. So to get the angle, theta is equal to tan inverse 1.33. That will give us 53.06 degree. So to calculate the active power now, so active power P is equal to voltage times current cos theta. That is 20 volts times 4 amp times cos 53.06. That is 80 watt times 0.6. That will give us 48 watts. All right, so let's move on to part 5. So it says to calculate the apparent power in the circuit. So apparent power, S is equal to the voltage times the current. That will give us 20 volt times 4 amp. That will give us 80 volt ampere. And that's it for this question. All right, so let's move on to the next question. So this is question 6 from the 2007 past paper question. Part A, it says, an 80 microfarad capacitor draws a current of 1.0 amp when 220 volt AC is connected across it. So it says calculate, part 1, the frequency of the supply voltage. So the first thing that we'll have to do is to calculate XC. So we were given the voltage across the capacitor. We were given the current as well. So from this formula here, VC is equal to I times XC. We can get the formula for XC. So XC is equal to VC divided by I. That is 220 volts divided by 1 amp, and that will give us 220 ohm. So now we can calculate the frequency. So from this formula here, the capacitive reactance formula, XC is equal to 1 divided by 2 pi FC. We can get the formula for frequency, where frequency is equal to 1 divided by 2 pi times XC times C. That will give us 1 divided by 2 pi times 220 ohm times 80 times 10 to the negative 6. That will give us 1 divided by 0.11. That will give us 9.1 hertz. All right, so that's it for part 1 of A. For part 2, it says the value of resistance connected in series to reduce the current to 0.75 ampere at the same frequency. All right, so the first thing that we'll have to do is to calculate the impedance. So impedance Z is equal to the voltage divided by the current. That is 220 volts divided by 0.75 ampere, and that will give us 293.3 ohm. So now we can go ahead and calculate the resistance. So resistance is equal to the square root of Z square minus XC square equal to the square root of 293.3 square minus 220 square. That will give us a square root of 86,024.89 minus 48,400. That will equal to the square root of 37,624.89, and that will give us a resistance value of 193.97 ohm. So that's it for part 2. For part 3, it says the phase angle of the RC series circuit. So to calculate the phase angle, tan theta is equal to XC divided by R. So that is 220 divided by 193.97. That will give us 1.134. So theta is equal to tan inverse 1.134. That will give us an angle of 48.59 degrees. All right, so that's it for part A. For part B now, it says make a neat sketch indicating the current and voltage relationship of the components in a RC circuit. All right, so as it relates to the current and the voltage relationship for the components in the RC circuit. So for the RC circuit, we know that we have resistors and capacitors. So the current and voltage relationship as it relates to the resistors, so current and voltage are in phase. For the capacitor, the current and voltage are not in phase. In this case, where the capacitor is concerned, the current leads the voltage. All right, so that's it for part B. All right, so let's move on to the next question. And this is question 10 from the 2013 past paper question. So part B, it says a capacitance of 10 microfarad is connected in series with a 5 ohm resistor across a 500 volt 50 hertz supply. Part 1 of B, it says draw the circuit diagram and the phasor diagram showing the relationship between the voltages and the current in the circuit. Here is the circuit diagram. So we have the resistor 5 ohm in series with the capacitor of 10 microfarad across a 500 volts 50 hertz supply. And here is the phasor diagram. All right, so that's it for part 1 of B. For part 2, it says calculate part A, capacitive reactance of the capacitance. So XC is equal to 1 divided by 2 pi FC. That is equal to 1 divided by 2 pi times 50 hertz times 10 by 10 to the negative 6. That will give us 1 divided by 0.0031. That will give us 322.58 ohm. For part B, it says to calculate the impedance of the circuit. So impedance Z is equal to square root of R square plus XC square equal to square root of 5 square plus 322.58 square. That will equal to square root of 25 plus 104,057.86 equal to the square root of 104,082.85. So this is supposed to be 86, not 85. So that is equal to 322.62 ohm. All right, so let's move on to part D. So it says to calculate the current in the circuit. So V is equal to I times Z. So from this formula, we can calculate I. So I is equal to V divided by Z, that is 500 volts, divided by 322.62 ohm, that will give us 1.55 ampere. And that's it for part D. For part E, it says to calculate the power factor of the circuit. So tan theta is equal to XC divided by R. That will give us 322.58 divided by 5. So that will equal to 64.516. So theta is equal to tan inverse 64.516. That will give us 89.11 degree. So power factor is equal to cos theta, which is equal to cos 89.11. That will give us a power factor of 0.016. All right, so that's it for this question. All right, so let's move on to the next question now. So this is question 8 from the 2004 past paper question. So it says a series circuit consists of a resistor R equal to 10 ohm and an inductor L equal to 0.5 Henry and a 100 microfarad capacitor connected to a 120 volt 50 hertz supply. So part A, it says sketch the circuit. So here's the circuit diagram where we have R1 connected in series with L1 and C1 across a 120 volt 50 hertz supply. So R1 10 ohm, L1 0.5 Henry, and C1 100 microfarad. So that's it for part A. For part B, it says calculate the following. Part 1, inductive reactance. So inductive reactance, XL is equal to 2 pi FL. That is 2 pi times 50 hertz times 0.5 Henry. That will give us 157.08 ohm. Part 2, capacitive reactance. So capacitive reactance XC is equal to 1 divided by 2 pi times the frequency times capacitance. That will equal to 1 divided by 2 pi times 50 hertz times 100 times 10 to the negative 6. That will give us 1 divided by 0.031. That will give us 32.26 ohm. All right, so let's move on to part 3. So it says to calculate the impedance. So when XL is greater than XC, impedance Z is equal to square root of R squared plus in bracket XL minus XC squared. That will give us a square root of 10 squared plus in bracket 157.08 minus 32.26 squared. That will give us a square root of 100 plus 15,580.03. That will give us a square root of 15,680.03, and that will give us an impedance of 125.22 ohm. All right, so that's it for part 3. So let's move on to part 4 now. It says to calculate the current in the circuit. Based on this formula here, V is equal to I times Z, we can get the formula to calculate the current. I is equal to V divided by Z. That is 120 volts divided by 125.22 ohm. That will give us 0.96 ampere. And that's it for this question. And that's it for these past paper questions as it relates to single phase series AC circuits.